Okay, did I invite you to unmute?
Now I think I can you hear me now?
Yep, I can hear you now.
Okay. So you might have to do that for Jared also when the time comes.
Right.
Okay. All right, so I guess it's 10 o'clock, so we'll just say good morning, everyone, and welcome to our Tech Talk on Cobots. Let me see if I can get back to my welcome slide here. Today we're gonna hear from University of Florida from Dr. Gloria J at Mechanical and Aerospace Engineering. And we're gonna have a little talk about and demonstration about cobots and what's happening in those with that area right now in her research lab. So if you don't know, I'm Dr. Marilyn Barger. I'm the Executive Director of FLATE, the Florida Advanced Technological Education Center. It's now part of the Florida Makes Network, and we serve the colleges and technical colleges in the state of Florida that support manufacturing. So today, I'm just going to take a couple of minutes to tell everyone about FLATE in case they don't know, and we'll have our Cobot presentation, and very exciting, we'll have a live demonstration from the University of Florida with their cobots to actually demonstrate what they're doing. And we'll just close up with some Q&A sessions or discussions, what anyone else has to offer or add to the conversation. We will be posting some resources in the chat, some resource links, and the recording will be posted also in a couple of days. All right, so a little bit about FLATE. Many of you know we were funded originally by the National Science Foundation at our host college, Hillsborough Community College in Tampa. We are now have funding from a variety of sources, including the Florida Department of Education and their Perkins State Leadership Grants to continue our work under the umbrella of the Florida Makes Network, Florida MEP. So our vision is just to drive the world-class manufacturing workforce education system, working through the colleges, technical colleges, and the high school career academies primarily. We do this in a number of ways. We work with curriculum reform and development, trying to make sure we have the best curriculum for supporting manufacturers at the different levels of our educational institutions. We do outreach and recruitment. One signature way we do that is through Manufacturing Month activities for students. And we provide professional development for our educators to help them be the best that they can for getting to and supporting manufacturing education. And lastly, we do some work in technical education research with some colleagues at the University of South Florida and Rutgers University as well. So I'm not talking about any of that today. Today, I'm going to present Dr. Wiens from the University of Florida, Director of the SAMM lab, and I've already forgotten what the acronym is, but I'm sure she'll fill us in a moment. And her research team, those are her students down below, Jared, Kalia, and Zarik, who are also with us today. I suppose they're the ones who will be answering all the questions that we might have for the team. So without any ado, I'm going to turn it over to Gloria to get started with some background slides about cobots and the work they're doing at the University of Florida, and then we'll move on to the demonstration. So pass this on to Jared for the demonstration. So I have to, in order to do that, I have to stop sharing. And there's Gloria, it's your turn.
All right, let's see, I've got the right thing in front of here, and I believe we now have the first slide of my presentation. Again, Marilyn, thank you for the kind introduction. And again, it is a pleasure to be here today and have the opportunity to speak about the use of collaborative solutions that give rise to a new frontier for robots and automation. My talk today will be a view of the technology landscape, the future trends for collaborative robots. We also call them cobots. I will highlight some of the state-of-the-art capabilities, the gaps in providing human-robot collaborations as a promising way to achieve increases in productivity while decreasing production costs. I have with me today is, again, my Cobot Research Action Team, which is in this Space Automation and Manufacturing Mechanisms Laboratory, which I call SAMM Lab. And Jared Flowers is my PhD student leading the effort. And then we have 2 undergraduate students working with us, is Kalia Bast and then Cedric George on that. So Jared will also present a live demo of his research later on in the talk on that. So hopefully with my talk today, it'll leave everyone filled with innovative ideas and a vision of pathways for their realization. So with that, I'm kind of start off with Industry 4.0 and 5.0, which are coexisting now. And with those two, they were creating a greater demand for human-robot collaboration in manufacturing. Industry 4.0 is technology-driven, which started around 2011 in Germany, and it basically advanced the concept of cyber-physical systems to be the cyber-physical production systems, where smart factories is one of the key associated initiatives with that. Industry 5.0 is more value-driven, where it's towards sustainable, human-centric, and resilience here. And so it had a scattering of starting out Industry 5.0 around 2017 with academe, and then as of January 2021, the European Commission announced the Industry 5.0 program that they have for their funding initiatives on that. So in terms of the Industry 5.0, there's 6 enabling technologies that they cited. And so 2 of those I feel were most relevant are the ones I have listed there in the slide, which is the individualized human-machine interaction technologies that interconnect and combine the strength of humans and machines. And then we have the artificial intelligence, which is to detect, for example, causalities in complex dynamic systems, leading to the actionable intelligence on there. Other way to look at it, Industry 4.0 and 5.0 is as a combination of robotics, Internet of Things, and smart manufacturing, where smart manufacturing is having the right data at the right time in the right form, wherever you need it throughout the enterprise on there. And with the Internet of Things, it's providing the connectivity. So it's basically taken the traditional factory automation that we've seen in the past and basically helping connect it and bring it into the smart manufacturing realm here. And this is evolving into cobots, which if you look closely in this PowerPoint, there is a human back in there. So basically cobots and humans are in this setting here, working side by side on that. In terms of the market trends, we saw in the pre-pandemic that cobots was really more of a market niche. So if you look at the bar chart there on the right, the little red there is basically showing you the niche where the units installed were still very low at that time and shared only 3.24% of the robotic space there. So, it did get a lot of media attention, but again, it still is that niche. As far as the benefits for cobots, a robot user typically chooses cobots when there is a need to prioritize safety, flexibility, low cost deployment, and fast return on investment. The resulting from the pandemic, though, has caused a rethinking of things due to the shortage of qualified workers, increased labor costs, and then subsequently, we're seeing now that collaborative robots are experiencing a rapid growth. Just last week, the robot manufacturers were on a panel was saying it's an exponential growth on there, as well as automate.org, which is a source for a lot of the market information I have, which is in the robot space, bringing different groups together on that. And Marilyn and or Teresa will put in the chat some links for those different websites that I have throughout the presentation. The primary driving force behind this growth is consistently decreasing the price, where now we see cobots are available for under 45K, and that's more viable solution over wide applications. And this is both inside and outside the factory setting, and for companies both big and small. And the advances in the edge computing has also made collaborative robots more flexible and easier than ever before to implement, because sometimes with this working on the edge computing is there's little or no program required just to install them, and therefore reducing a lot of the integration costs. So increasing the flexibility opens up a wide range of new tasks and applications that collaborative robots can effectively automate. So in terms of research, you see the plot here on the right is showing that human-robot collaboration, which is what we call HRC, is more dominant in the research realm of academia on that. So I haven't really said what is a collaborative robot, which we call Cobots as the short name for it. And it's basically a robot intended to physically interact with humans in a shared workspace. It combines the strengths of humans and robots. So where the cobots typically are responsible for the repetitive and manual task, and the human worker is more responsible for the complex and thought-intensive tasks, utilizing their skills for intelligence and problem solving on that. In terms of the use of cobots, there's 4 main collaborative levels that are depicted in this slide here, where level 1 is the safety rated monitored stuff, SMS, and this is generally used for one of the other levels on there. And SMS is basically a monitored standstill. It stops whenever the robot application, whenever a human enters a space, it's detected, but it maintains the power on so that once the human leaves that space, then the robot's action can resume quickly on that. Level 2 is the hand guidance. So you'll see some in the videos the use of hand guiding on that, where the human basically, it's also another way of teaching the robot, is taking it through its motion that you want it to do, and then it records that, but also doing it for a shared task. The SSM, which is speed and separation monitoring, is really an advanced level of SMS because it basically divides up that intrusion space into different zones, where if you're in the green zone, okay, the robot just slows down. As you get into the yellow zone, it slows down further. And then when you're in the red zone, then the robot application stops there, waiting until the human leaves the space there. And those are all defined by the user on different levels of threshold here. Another popular area is the power force limiting, which involves an expectation of physical contact between the robot application and the worker, and this is permitted on there. And let me go to the next slide here. Oh, back to this other slide, I want to point out also is the industry goal is to have fenceless robotics here. Is why you have the cobots coming in. So you don't have all that floor space taken up building fences around everything on that. In this slide, I have, again, a little bit more of the definitions of the different levels, but you also see that this graph is showing you the usage of those. This is 2018. That was the most recent I could find in the published out on the web on there. But basically, this is in the reports. So this is kind of shows you that it's still a mixture of all those different levels being used. And in terms of the research, you've seen that a lot of it is going to be on sensor monitoring, as well as the power force limited applications. And actually all 3 of these on there used in research. Okay, in terms of the classification and the different methodologies for human-robot interaction, we have shown here is kind of 4 of these here. So you have the top-down look at it, as well as over here, kind of showing you with bubbles how much the interaction between the human and the robot. So coexistence is basically you're bringing the 2 spaces, the human worker and the robot, close within proximity of each other, and then they do not interact with each other on that. If they do, there's the yellow zone is kind of like the Passover zone here. The synchronized is one where the human and the robot have same workspace, but they are at different times accessing that workspace. And then if you have cooperation, then you see them, they are accessing the same workspace, but they focus on separate tasks. on that. So again, these synchronizers are not at the same time, but where these cooperation that they are exchanging back and forth here. Okay, so for the collaborative one, this is where you have the human and the robot have to work together. The task is one together, executed together, and so the one action of the other immediately has consequences on the other. So, and again, we have sensors and everything to help with that. As far as the applications, it's pretty large range here. Assembly is predominantly what's being studied in the university research as well as human assist. But again, there's applications you can see out there of the different areas here. And then of course, what you choose if you're going to do cobots is what type of production do you have? Do you have a lot of variance in your product, or is there a high volume? So that also is a driver on when you're deciding, is that the right solution for you? So here, this plot depicts that, where the green here is the collaborative space there. One of the challenges for deployment, of course, is unraveling the work assignment. What does the human do? What does the robot do? And how do they interface? That is one of the biggest challenges there. As far as deployment, the robot manufacturers and integrators have said that it takes, depending on how complicated the task is that you want a cobot for, it can be a few weeks or it could be up to 6 months, but it is much shorter turnaround than the more traditional ones. As far as sensors, we have basically the more collaborative space will be a whole combination of sensors. So it'll be a sensor suite, and again, it's application driven, what you need. So if you see up here on the top on the right diagram, it shows some cameras up here. So they could be color, depth, thermal cameras, or maybe LiDAR, time of flight cameras could be up in there. And you can have them actually in different spaces within the workspace. It doesn't have to be in the ceiling. When you're having the touch, of course, you may have some type of haptics or tactile or skin sensitive. Sensitive skin is actually being seen now in cobots coming out, being available. Audio, speech, and you also see in the videos later hand signals. The biosignals are starting to become of use because they're being used to predict the, from your biosignals, are you having anxiety, fatigue, to help interface better the task in the robot. Motion sensors is another, and they have these smart bands, wrist and the arm bands that are being wear. Of course, you have the Google Glass type glass. And then ender tooling is another area for helping with cobots, is because the ender tooling could have the special sensors in there to help achieve a task, so for example, like metrology. And the smart IDs helps the robot know, okay, which human am I working with? Because humans work differently. And if the robot has learned that, then they can behave accordingly. All right, so these are some applications here. And I'm going to try to do this with, these are video links behind there, but there's also, I think Marilyn or Teresa might have put those in the chat. I don't have the chat open to see. Oops, now I think you can see that. Get these other different screens here. There's Cobot Assist, and which is like, here is polishing a car hood. It's actually one of the larger cobots that are available in industry. You have lifting heavy, like a heavy assembly action here, whereas this is a mobile unit here. You have palletizing is very popular on there. So I'm going to try to go to these, and this is where the challenge is going to be, because these are videos which shows you all those different modes as well as a real end user use here. So one is KUKA is the first one, and then the FSK Industries using Universal Robot is the next one, and then SC Automation and Fanic Robot being used in dispensing here. So let me give this a try, and I'm going to see what happens here. And you need to let me know, I don't know if I can get, Marilyn, can you give me a thumbs up, or Teresa, if you can see this or not? And
it's working fine. I can see and hear it.
Okay, all right, so I'm going to try full screen so you can see it a little bit better on here. And it should be going now. So this one is a really good video here.
Intelligenz.
All right, so I think you now see my PowerPoint again. And so I'm going to go to this one here. I think I might have to close the screen. Whoops. Okay, so I got this one here, and it's this is already one. So we can go dive in. Okay, and my last video is this one here, which is I'm not sure if you can still hear me, but this one also shows how you shrink the workspace. Okay, so oops, I hit the wrong thing here. There we go. All right, thank you. Back to my slideshow now and everything. You can hear me. So this is just some of the leading cobot manufacturers here. You just saw videos from 3 different ones of their end users using their robots. In terms of challenges, there's still a lot of challenges still in cobots, but you see there's a lot of benefits too that industry is actually seeing and realizing. Priorities, of course, in the challenges and pushing the state of the art is you have human safety and productivity are both upmost in terms of priorities. However, they can be conflicting because for safety, sometimes you have to stop and wait, and then that reduces your productivity. So trying to find the right balance there to actually enhance your productivity or at least respect it so you don't have too many delays due to the human and robot interaction. There is physics and fundamental limitations. The task complexity, as I mentioned before, is unraveling that task definition to be most effective. And then building that trust between the robot and the human. It's not just the human building trust in what the robot's doing, but also there's an application looking at how does a robot build trust in what the human's doing so they can have better reaction or interaction between each other. So I'm looking at advancing the proactive and reactive of the robot responses to the human motion, as well as vice versa, because I look at it as a two-way communication is on the horizon on that. So there's risk assessment, there's human and robot intent, sensory feedback is important. So the more we can do that, one of the integrators from a webinar I went to mentioned that they use monitors to show the human that yes, the robot is seeing them so that they feel confident that the robot realizes they're there and build that confidence level. Other thing is integration, and I'm changing the name of AI. I call it augmented intelligence for me because I'm looking at the robot control end of the whole human robot collaboration scenario. And so basically we need to be bridging that sensing and AI as an artificial intelligence with mechanical and physical necessities to successfully augment the robot's awareness and intelligence, which ends up with augmented intelligence of the robotic system on that. Of course, we have safety, as you can expect. There's ANSYS and ISO standards that one must meet in using cobots. In addition, the automation robotic, in addition to automation and industrial robots, there's also the underlying standards. There's also the ISO TS 15066 standard, which is specifically for cobots. This org chart on the right is showing you that we have different agencies within the government that are working on these standards and enforcing those. Of course, you have OSHA, which everybody is familiar with. It's also in the news these days. And then you have under CDC is NIOSH, which also has, they've been looking at, highlighting the human robot collision limits, safe collaborative working space environments, and basically evaluating the potential benefits and risk of robots in the workplace, as well as conduct workplace interventions to prevent robot-related injuries and develop safe interactions between humans and robots. And my understanding from NIOSH, when I was talking to them, they actually are in partnership with one of my colleagues here at the University of Florida that has an NSF award, and NIOSH was a part of that initiative. In terms of research, okay, so with recent advances in sensing and computational intelligence and big data analytics, they have rapidly been transforming and revolutionizing the manufacturing industry towards robot-rich and digital connected factories. So collaborative robots of the future are now expected to take collaboration and productivity to an entirely new levels. However, there's still the effective, efficient, and safe coordination between humans and robots on the factory floor that still remains a significant challenge. And further complicating matters is that the robot is cooperating within a heterogeneous manufacturing environment that has both robots, humans, as well as equipment that it has to interact with. Collaboration when the human worker and the cobot must execute a task together, then the action of one, again, challenges on that. So with that, we look at one of the most useful changes that can radically change collaborative robots would be an increase in interactivity. And then what's considered the holy grail of collaborative robots is achieving a form of true collaboration. So, and to enable the safe and effective human-robot collaboration, seamless integration and sensing, cognition, and prediction in the robot controller is critical. And for real-time awareness and response and communication is what's needed too. So how do we get there? Well, we need to integrate sensory information into behavior models and controls. And this will enable context-aware applications and safe workspace sharing. In this slide, this is my colleagues from Italy, the National Research Council of STIMA, which is STIIMA, which stands for Institute of Intelligent Industrial Technologies and Systems for Advanced Manufacturing. They are basically the equivalent for Italy, what we call NIST here in the United States, National Institute of Standards and Technology, which all of you are familiar with because FLATE is connected to Florida Makes, which is a MEP program within the NIST agency on that. Here, this slide shows the researchers at STEMA. They demonstrate the use of RF signals, noting that a lot of systems with devices within the manufacturing facility emit RF signals. So why not use that information to help determine where is the human in that space? So those RF fields and also with time of flight cameras, you can detect where the human is, and then you also can use that in a dynamic way to determine is something, you know, like did a human fall and they need help? You can have that type of sensory just by looking at those fields and the time of flight data there. This slide actually shows two of their videos where they were demonstrating the ISO standards for cobots. The one video on the left is a robotic system operating in the speed, separation, and monitoring mode. And as you notice, you see the human is actually giving hand signals there, which are interpreted by the system there. And you actually saw the human push on the robot to activate it, to get it moving, to doing a task. And it's showing you a very collaborative task there, example there. The one on the right is the power and force limiting level of operation. And I don't know if you saw already, because it's two videos, but at once, they had where the robot bumped his shoulder, and so it sensed that there was a bump and had a protective stop, which required a manual override. This is where you have a quasi-static contact is occurring where it's a passive gripper mechanism and it had a protective stop. And then you have a hand guiding with speed limiting, where if they move it too fast, then it will stop too. And this is again another interaction with the gripper. And you notice on the left, you also see the cameras picking up where the person is in their hand signals too. So again, these are some applications of STEMA. We work there, again, they're like NIST to us as they are to Italy on it. And they are collaborating with us on our research here. Okay, here is another demonstration of their work, which is basically having the human go through its motion of performing the task. It's picking up through camera tracking and getting that information, and then that data is then fed into a path planning algorithm that's done offline. And what it does, it determines volumes where, which we call HOVs, human occupied volumes, and each of these volumes have different probability of the expectation of will a human be in that space during at different times of that motion. And so they use that to help path plan, so the robot will then decide, do I take the risk that the probability is so low that the human will be there? I think I can safely move there, and the likelihood is small that I'll have a collision. Of course, there will always be that protection, underlying protection with collisions too with cobots. Anyway, so that is an offline version of path planning on that. So trying to move more to real time and online type advances in cobots. This is a project that I have here at the University of Florida, which is funded by the National Science Foundation, National Robotics Initiative. It is with the it's 4 universities, University of Florida, and we're partnering with Case Western University, the Missouri University of Science and Technology, and Stony Brook University. We partnered with Comal, and then we're also looking for other industries to partner with us, because part of our project is it's like an integration type NSF project, which means we need to integrate and demonstrate our achievements in the research in a real industrial type setting on that. We also have STEMA there, which also have their R&D labs where we will also demonstrate in their facilities. And then we're part of Manufacturing USA, which is this Manufacturing Innovation Institute network. On that is part of our classification, because I'll be partnering with, the goal is to partner with ARM, the Advanced Robotics Manufacturing Institute, to put on workshops that brings stakeholders together in the collaborative robot space, as well as the AI space that work in collaborative robots on that. And so we'll be having some workshops probably in about a year from now. Okay, so this is our team there. And then how we're looking, dividing up the work. University of Florida is the action team, because we're working at the robot control level, where our colleagues are working at perception, cognition, and prediction, and they're taking more an AI approach, bringing that information, and they're supposed to providing us the prediction of what the human is doing, so that we can have a better action of the robot to accommodate for any deviations from an expected motion from before. So we want to basically identify those, take that data, and come up with the right reaction and use it. Whereas if we can get it as far enough in the future, then we can actually do more planning ahead of and basically prevent collisions from happening that would otherwise have happened on that. And also we're building trust there. Okay, so this is the Stony Brook, where they're basically taking all that vision data, and through AI, they're finding out what's most relevant on there. And then you have with the Missouri group, they are looking at hand gestures and so forth for communication, as well as doing some prediction there. And then the Case Western group they've done some skeleton tracking of humans, and then doing some neural nets, recurrent neural net in this case, with probabilistic characteristics there to eliminate uncertainty and to minimize mistriggers. And they are then providing predictive information, where then we take that predicted, and if we know, depending on how far ahead, we might be able to then, in simulation, while the robot's performing, go ahead and simulate, is there going to be a collision from what's being predicted, and what would be then the reaction that the robot should take, or should it be communicating with the human to have the human take an alternate reaction? There is what our ultimate goal in the end is, having two-way communication. We have risk of passage on there. Basically, if the robot's going to do some type of maneuver, is a human going to come together, like it's shown, like you're trying to move between the arms, some task, if they're going to bring their arms together, and will that cause a collision, or is it had time to do the task? So those are the different things that we're doing. And again, as the action team, we do have our control architecture here, where we have our framework is a proactive, adaptive, collaborative intelligence, and basically using it both as online planning as well as in real time, doing the different combinations. It allows intelligence switching between control types depending on what task is being occurring and what the prediction is coming in from the human motion here, either perceived or predicted. And then from that, we have then a safe robot human interaction there. And we basically are segmenting the task up into subtasks, so that certain tasks a robot should not stop in the middle of. For example, I always give my students, if the robot's pouring molten aluminum into a mold, you don't want to stop in the middle of a pour, because it will keep flowing on there and cause a greater catastrophe than if you would say, hey, communicate with the human, we need to take it, you need to pause because this I have to complete. So basically evaluating the behaviors of and the type of task is how type of behavior, how the robot will react to that interaction with the human there on both sides. And the other earlier study we did is also how far in advance would you like to know if a collision is going to potentially happen, so that you can plan and have a smoother motion here. We actually found if you waited too late, the joint constraints and all that caused more a rough motion there, and actually you lost the productivity. So it's not a linear relationship here. So with that, I'm going to turn this over to Jared, who's going to give a live demonstration on that. And so let's see if I can stop my sharing and let Jared take over, because he's going to take you to the lab. Unless, Jared, did you want me to cover those 2 slides?
I can pull up those 2 slides.
Okay, because I can quickly share.
Yeah, hello, my name is Jared, and I'm here in our lab today at UF. I'll have a demonstration to show in a minute, but first I will introduce our test bed and introduce our research a bit. On the left image in this slide, you can see our 6 degree of freedom robot manipulator sitting in the middle of the image, sitting on the table. And then just to the right of the robot, you see some of the computing hardware that's used to control the robotic system. And from this image, you can also see where the worker would stand relative to the robot in our test bed. And since this image was taken, we've also added a couple of cameras and some additional computing hardware. The image on the right also shows me interacting with the robot. This image comes from one of our more recent publications. The demonstration that I'm going to show today is representative of a human-robot collaboration in a manufacturing setting. In a manufacturing setting, human motion could frequently deviate from nominal motions. So in the demonstration today, I will randomly put my arm in the path of the robot to demonstrate some of these unplanned human motions. When this occurs, robots can respond proactively to avoid production delays. And in the more recent publication I mentioned, we addressed the problem that trajectory planners couldn't generate a new robot trajectory when the goal pose was blocked by an obstacle. And so in the method that we proposed, the next best robot pose is generated, which is a pose where the robot can go to wait while avoiding collision, but still being as close to the goal as possible. And the goal was to reduce the increase in production time due to this obstruction. So the image on the slide actually shows that my arm is blocking that goal, and the robot went to the pose you see there to wait until I'm out of the way. And so now I will share the screen for the live demonstration. Before I start the demonstration, I will show some of the user interface that we use in our lab. We've developed this web-based user interface. I'm currently on the operation tab, which has a start cycle button to tell the robot to start the task. It has a continue button because at various points in the demonstration task, the robot has to stop and wait for the user to say it's okay to proceed. There's also a repeat cycle button to make the robot do the same task that it just did. There's also a cameras tab, and in our lab, we have a depth camera just to the left and to the right of the robot, and we're using those to sense the human location in the work cell. So the 2 video feeds at the top of the screen come from the left and right cameras respectively. We're also using skeleton tracking software called OpenPose, which is taking the video feeds and it has neural networks inside of it that are estimating where my joints are located. And then the tracking software is also overlaying the colorful line segments to represent my skeleton. So in the video feeds, you see those colorful line segments that are kind of following me as I move. And this allows us to have an estimate of the 3D location of all of my joints. And then the bottom feed shows it's a virtual video feed of what the robotic system is seeing and planning around. So you see the robot manipulator sitting on top of the table, which is blue, and then you see my 4 arms represented as the 2 green cylinders. So like if I move in the top 2 video feeds, if you see me move my arm off to the side and you see one of those cylinders follows it. So you can see how these 3 displays are related. So now I'll describe the task the robot is going to do, and you can watch the 2 top video feeds to see what I point at. The robot is going to is going to pick up this green block here, and then it will rotate around to put the green block on top of the blue block here. And then at this point, I'll have to reach in and snap these blocks together. They're like little Lego blocks. Then the robot will pick up the block assembly and rotate around to hold it out at an inspection point here. And then if it looks okay to me, I'll push the continue button to tell the robot to put the assembly down and go back to its home position. Additionally, I'm actually I start the robot from my iPad and push the continue button here. It's using the same displays that I just showed you. So I will go ahead and tell the robot to start. So right now it's moving to pick up the green block. And now I will put my arm in the way. And it sensed it and stopped. And it has planned a new trajectory to try and go up and over my arm. We do have a little bit of error in sensing, so it didn't go as high up and over my arm as I would have liked, but now I will reach in and snap the blocks together. And then I push the continue button. And oh, the robot sensed that I was in the way. So now it would have picked up the blue and green blocks. And then it sensed that I was too close. So I've actually programmed it to go back a little bit before it starts to go back to in the direction it was supposed to. And this is the inspection point where it's supposed to be holding the blocks. Sometimes unplanned things happen in HRC. So I put the blocks in the grippers and I'll say continue. And then if I put my hand over the robot, it stops again so it doesn't hit me. And now it resumes motion and it will head back to the home position. I will also show some of the other tabs in our user interface that we use for research. We have a calibration tab that allows me to, when we power up the robot, I have to look at all the joints and tell it when it's in the upright position. We also have a position tab, and this tab gives me a virtual teach pendant, basically. It allows me to enter the joint angles for the robot. I can also enter end effector, XYZ, roll pitch, yaw, and have the robot go to that position, as well as controlling the gripper and having some preset positions. We also have a tasks tab where we can input subtasks required to complete a task. So this is just a few subtasks, which would be part of a larger task for building a small engine. So the subtasks are at kind of a general level. And then inside the subtasks are motion segments. So this is the list of motion segments the robot just did for moving those blocks around. The segments have start and end waypoints that the user could put in as joint angles or desired XYZ, roll pitch, yaw. And as Dr. Wiens said, the motion segments also have a behavior for the robot associated with them. So when the robot had picked up the green block and was moving to put it on the blue block, that was a non-restrictive type of segment where when I put my arm in the way, the robot is allowed to plan a new trajectory that goes up and over my arm. However, there's also restrictive segments, such as when the robot had picked up the block assembly and was moving to the inspection point. During that segment, if an obstruction occurs, the robot just has to stop and wait. It's not allowed to deviate from its nominal plan. And then there's also some diagnostics in this user interface. Like the skeletons tab here shows me the skeleton that's generated from the left and right cameras, as well as a skeleton that's a fusion of the best data from each camera. So like right now you see the blue skeleton looks it looks messed up because my left arm is behind the robot in that skeleton's view. There's also utilities to stop and start various parts of the system, and also recording data for research and downloading the data files. At this point, I'll show a video from one of our more recent publications.
Jared, I'm not sure if we might be running low on time. Is that a real short video?
Well, I'll just show part of the video. So this is the robot going to the next best pose, which we mentioned. So in this clip, the robot's doing the same block stacking task. I put my arms in the way, but my right arm, which is holding that yellow block, it's blocking the goal pose. So normally the robot couldn't do anything here. It would have to stop and wait for my right arm to move. However, with our approach, the robot moved to its next best pose, which is here. And then when I get out of the way, it goes and stacks the blocks. And it's important to note the next best pose is closest to the goal in terms of angles and not actually visible distance. And so the live demonstration and the video that I showed here show just part of HRC. HRC goes well beyond just avoiding collisions. And so in the future, we will work on incorporating AI and other algorithms into our system. So now I'll turn it back over to Dr. Wiens. So I'll stop sharing now.
All right, thank you, Jared. And so kind of closing things out, some takeaways that you should see with this presentation, hopefully today, is again, there is benefits in having cobots from safety, space saving, flexibility, ease, and low cost deployment, as well as fast ROI. Quoting Paul Santi, as I have on the slide here, that he emphasized with his customers that you design your application for collaborative, but you don't force it, you enable it. And then remember that there's always multiple forms of collaborative, and you get the greatest value from the solution that meets your goals. Other takeaways I want to add is that keep an open and innovative mindset, because technology keeps advancing, and with new sensors and new devices and stuff, it actually enables you to maybe do something that you couldn't do yesterday, but now you can do today. So always keep an open mind there, because you can end up with greater and improved environments. And then one last slide here is my pitch. I actually have a call for volunteers. Part of my NSF project is to have a broader impact. And so we're developing a educational module, which we hope that you would want to adopt into your educational programs. Again, it's not a full program, it's more a module that is focusing on cobots and AI and that integration, so that anyone can pick it up and incorporate it into their advanced training education programs. And Kalia and Jared are going to be leading that. So Kalia will probably be their main contact in terms of as we keep going forward, because it's kind of her lead project on there. But I am looking to form an advisory board. So here are some names that from the previous meeting where I pitched this that Flake had. I believe I have Sam on board, and maybe Shirley. I think Shirley was in those in attendance today, and Kevin. I'm looking forward, and even Stephen. I know, Stephen, I hadn't followed up yet with the information that you'd asked for, but I plan to. Anyway, I'm hoping that you'll would like to join my advisory board, as well as any others out there or anyone you can recommend that might add to the advisory board, so that we develop a module that's useful for everyone. I mean, it covers that niche of cobots and integration with AI, and it's useful for you, and it hits the areas that we need for training. So anyway, that's my pitch. And so with that, are there any questions? And I guess I should stop sharing screen.
Well, thank you, Gloria. Any questions anyone has in the chat? I think if you were interested in the advisory committee that Gloria just mentioned, one way you could do that is put something in the chat. You can also email her directly. You want to put your email address in there too, Gloria, or Callie's if you want her to be the contact. That would be fine as well.
We'll start with mine, and then she'll start with organizing meetings and stuff. She'll probably have meetings like at least maybe quarterly meetings. It all depends as we bring it all together on this. So I'm going to put my email in the chat.
Okay, great.
All
So-
right. Steve is said he'd like to join. Okay. Okay. At least get more information. Okay. I will do so. Thank you.
And I
Steve.
want to join. I didn't see you put my name on your list yet. But,
Right.
let's
So
see.
please,
gonna-
in case I don't capture all the chat here. Okay.
Okay, we'll capture the chat and share it with you. And otherwise, anyone can contact me as well if you missed the chat or whatever, just want to double check, that would be more than fine to contact me and we'll get you connected to Gloria and her team. I'm trying to get to share this in a bigger mode, but I'm just going to move right now. I did have, we had more links, I think, in the chat, but here are the links, some of the links that Gloria provided here today for resources for you. Of course, the recording will be posted as well. And before we close, I still don't see any other particular questions or comments. We do have 2 more scheduled events coming up after the holidays now in January and February. And January 20th, we're going to have from another great university in Florida, Dr. Nancy Diaz-Alcayed from USF here in Tampa, and her team, and they'll be talking about an Industry 4.0 case study for tool condition monitoring for CNC. And Dr. Diaz does a lot of work in the sustainable manufacturing arena. So this is all about making sure that we're focused on sustainable systems in manufacturing and obviously other aspects. And then in February, we'll have Dr. Dae-Sung Woo from University of Central Florida. Seems like I left that part off here, with applications of machine learning and smart manufacturing. So he has a couple of case studies he's going to talk about, how we add in machine learning as one aspect of artificial intelligence to smart manufacturing systems. So we hope you'll all be able to join us. There is some more details about these 2 upcoming sessions on our website. You can check that out to get more information. And thanks again, everyone, for coming today. And hopefully we'll have a great Thanksgiving and wonderful holidays, and we'll see you in the new year. Thanks, Gloria and your team, Callie, Jared.